answer a couple other questions. I have finished the adjustments for the curving of the exam, and the true exam points are on tracks. So I have your first week's homework grade and the curved exam grade on tracks. It's weird, it's out of 240 points, but that's the way the weighting system works. But there should be an assignment for the actual percentage-wise on there. And so if you did great, good, keep trying hard. If you did okay, keep trying hard. Things are gonna get a little different. And if you didn't do well, go ahead and email me and we'll set up a Zoom and try to figure out how we can get everybody up to speed, okay? So, the last exam had 20 questions on it. The next exam will have 30 questions on it. So I'm gonna make it a little bit longer such that you can take a little more time to do it. And then the following exam will actually be a little bit longer as well. So I'm just ramping up how long the exams are with the number of questions, basically. So we'll have 30 for our exam this week, and then 40 for our exam next week. And then depending on how people do on time, if people are still doing well on time, then we'll probably keep that 40 questions. And then the final will be 60 questions because we have a longer period of time. So any questions on that?
Do you have, what was the average? Where did we kind of fall as a group? 74%.
So that is actually what my target is, 75% for the class as a whole. And that gives me a really nice curve. As far as if you look at the statistics, well, I looked at you can't look at them, but I looked at my statistics. I had a nice curve on there. You know, not too many hundreds and not too many lower than passing grades. And so that was a pretty good statistic wise. So I think overall it's a great start. And when on our next exam, that'll give me a little more data to see how good we're going. But overall it's doing pretty good. And the homework should be, what I do is I actually do the whole week's, the 40 points of homeworks all in one score. So you'll see it as a week, not an individual. But those individual numbers are correct on on Top Hat. That is the number out of 10 is the correct value for that. So, but the exam value is not, because the exam value is curved. So don't worry about that. All right, I'm gonna start by sharing my screen. Well, and if you have questions, go ahead and type them into the chat here. I wanna get through the next 3 goals here, which is also the goal for chapter 6. It appears I didn't change that on here, but okay. So for this particular set of goals, what I wanna do is work on some of the definitions and looking again for mirror planes. The definitions are kind of, you know, it's a defining element of it. Just getting the 3D drawing is part of it, getting R and S is part of it, knowing what the different isomers are is the next part of it, and then finding those symmetry and mirrors is the last key of the puzzle. Okay, so the overall set of relationship with isomers is the idea that if you have different compounds, you can have different compounds with the exact same molecular formula, okay? So there's a couple different ways we can do that. We can hook them together differently. If we hook them together differently, those are called constitutional isomers. If they're all hooked together except for their place in space, meaning that all the same bonds are in all the same places, but you just swap 2 of the bonds, then we have stereoisomers. Now notice we have stereoisomers for things with double bonds too. We have cis trans, and those are exactly the same connectivity. All we've done is switched 2 of the bonds. So those cis and trans alkenes count as stereoisomers as well. The ones we're focusing on in this chapter are the sp3 hybridizer tetrahedral stereoisomers. Okay, so within that set, we have 2 types. We have the enantiomer, which is anything that has a single chiral center that you can draw a mirror image of that is non-superimposable. So typically we think of enantiomers, you can only have 2 if you only have 1 stereocenter, okay? Once you have more than 1 stereocenter, now you have diastereomers, okay? Now, di does not mean two. Now, if you have two stereocenters, then yeah, you'll have two sets, but it's 2 times the number of stereocenters you have. So diastereomers can be 2, 4, 8, 12, 16, you know, it just gets really big numbers really quickly. So, but the definition for enantiomer is 2 compounds that are just different in space. Everything else is identical. Diastereomers are 2 types of enantiomers that are connected except for that way they're connected in space. Okay, so that's an important relationship to keep in mind. Enantiomers are always 2, diastereomers are 2 times the number of stereocenters you have. Okay, so again, the enantiomers are where you can draw that mirror image, and I showed you some techniques for correctly drawing that mirror image and then being able to translate them to make sure they're non-superimposable. And so then, but again, that only has 1 stereocenter. If you have more than 1 stereocenter, then you have 2 sets of enantiomers. And notice the spatial difference between this compound on this side here and this side here is that all we've done is taken 1 of the functional groups or 1 of the priority groups and switched it to a different place in space. That's how we go from the 1 set of enantiomers to the 2nd set of enantiomers, is moving 1 group in space. Now, once you move that in space, then this one right here is not the mirror image of it anymore, and you have to draw its new mirror image. Okay, so that is something that I want to make sure that's clear in your head. Okay, so once you do that, you want to think that enantiomers are like pairs, like hands. They are in pairs. Diastereomers are in different things. And again, to have enantiomerism, you must have those 4 different things bonded to carbon. Double check, make sure they are all different, and make sure you can prioritize them in correct order. So anytime you have 4 different things bonded to carbon, we call that a stereocenter. However, you can have, as long as you have a tetrahedral center, you can have 4 different things bonded to silicon or nitrogen or whatever. The key is 4 different things bonded in an sp3 hybridized system. But for us, we're only going to deal with carbon. Okay, I got to move this thing out of my talk window. All right, there we go. Okay, so that being said, we looked at how to use our mirror image and draw our mirror and draw that mirror image correctly. And that was an important function. Now, if we go down the path and look at it and say, oh, look, there's 4 things hooked to this carbon, let's draw the mirror image. And we get all the way to the point where we've rotated at 180 degrees and they overlap. We are not chiral, okay? If we do the rotation and you do have 2 things that overlap, they are superimposable, that means it's achiral or without chirality, okay? So we need to, that's, you know, kind of why I want you to double check right when you start assigning chirality to make sure they're different groups. I caught many of people on a quiz where they're trying to assign chirality to something that was achiral. So, okay, so after it's non-superimposable, we have a stereocenter or that stereocarbon or that chiral carbon. All of those really mean the same thing, the carbon with the 4 different groups on it. If it has only 2 different groups on it, it can have 4 different groups, but sometimes that image is superimposable and therefore it is also achiral, okay? Now, the enantiomers always come in pairs. Diastereomers always come in sets of multiples of 2, okay? So let's get into that. So a single stereocenter gives you 2 possibilities. 2 stereocenters gives you 4 possibilities. 3 stereocenters gives you 8 possibilities. Okay, so it multiplies 2 times the number of stereocenters you have. That's why, but they're always in multiples of 2. And what you do to switch from one set of enantiomers to the next set of enantiomers is take a single high priority group and swap its place in space, and then draw the mirror image. So that way you can do multiples of any of these. If you really wanted to go down the rabbit hole, you could go take any compound and figure out exactly how many stereoisomers it has and draw them all. However, any more than 2 is just kind of practice. Okay, so again, when we have these sets, if you have 2 stereocenters, you end up with 4 isomers. The thing you have to double check in the 4 isomers is there a mirror plane somewhere? Is there a plane of symmetry somewhere in one of the molecules? In the set here, we don't have to look too hard for that plane of symmetry, and I'll show you why. Here, in this group here, we have a CH2OH, and in this one we have a CHO. Okay, that means this could never be the mirror image of each other. So in the case where we have 2 wildly different functional groups on them, we don't have to go searching very hard for those planes of symmetry. The fact that we have these 2 different groups say, okay, we probably will not find that plane of symmetry. But when they start looking very similar or start getting rings where we have a symmetrical ring, now we need to start looking for those planes of symmetry. Okay, so when we go to that, when we change that functional group from that CH2OH and CHO to 2 groups that are the same, we have 2 carboxylic acids now, one at the top and one at the bottom. Now when they are the same on both sides of the ends of the molecule, now we need to start looking for that plane. Okay, and what we see is when we have the OH groups on opposite sides of the molecule from each other, we cannot see that plane because they'll mirror, the hydrogen is going to mirror an OH and the OH is going to mirror hydrogen. So we know we don't see that here. But now, once we have it here, these OHs can mirror each other, but now this last group, this carboxylic acid can mirror itself, and the hydrogens can mirror itself. So again, if we have multiple different functionalities, we're less likely to see that mirror plane. When we start seeing one side of the molecule look exactly like the other side of the molecule, that's where we're looking for a plane of symmetry. And if we have that plane of symmetry, that means that these 2 compounds, even though we can draw them as mirror images, are superimposable. And because they're superimposable, that turns them into the same compound, or a meso compound. Okay, what that means is that the compound and its mirror image are superimposable, so that means it's one isomer. Okay, so we still have our pair of enantiomers here in our meso compound. So with 2 stereocenters, we end up with a total of 3 different compounds because the one has that plane of symmetry. Okay, so those are our definitions on the different isomers and how to identify which ones you have to pay closer attention to. Okay, so any questions on that? Because the last thing I want to talk about is planes of symmetry and things to make you think twice. Okay. Everybody still there, right? Okay, still have 15, that's not bad. Okay, so our last thing is finding symmetry and mirrors, okay? So a plane of symmetry can be anywhere. It can pass through bonds, it can pass through atoms. Like for example, in this one right here, one of the reasons this compound, people say, oh, 4 different groups, hey, it must be chiral. But if we look at this here, really, these 2 methyl groups are the same. But we can also draw this plane to be cutting through atoms. We're actually cutting through 4 atoms in this plane to find that plane of symmetry, okay? So you can cut through atoms, you can cut through bonds, you can cut through atoms and bonds, okay? Don't worry about where you find that plane of symmetry. If it looks the same above and below, you found a plane of symmetry, Okay, so in the case of our groups here, we have a methyl group and a ethyl group and an OH group and a hydrogen. Okay, 4 different groups. That means we definitely will have no place for that mirror plane of symmetry to be. Okay, so we definitely will have a set of enantiomers in this compound. However, even if we do this rotation, that experiment in rotation where I was showing you how to rotate the things 180 degrees to make sure they're not superimposable, when we do that with this system, we can line up 3 of the atoms right here. These 3 atoms and these 3 atoms are lining up just fine, but the last 2 will always be swapped. Okay. In fact, you should be able to line up at least only three of the different atoms in the bonding to that chiral center. You will be able to line up at least 3 atoms. It's what happens to the last 2 atoms tells you whether or not it's chiral and or which enantiomer it is. So if you redraw it and you can't line up 3 things, try again, because you need to line up at least 3 of those atoms. They should overlap, and it's just then the last 2 is where you make your decision as to whether it's superimposable or not superimposable. Okay, so I actually already did this on the other functionality. I didn't think I did that, but I did. Okay, so let's talk about that meso compound again. First thing we think of when we think of a meso compound is that we have the same functional group at the top and the bottom of the molecule. That means us, watch out, we have to look for a plane of symmetry. Notice in this compound here, the plane of symmetry cuts through a single bond, okay? It doesn't cut through any atoms, but it cuts through a single bond. That happens a lot in the linear compounds. When you have cyclic compounds, you're probably going to cut through either 2 bonds or a bond and an atom, depending on whether it has an even number or an odd number of carbons, okay? When you have a 5-membered ring, what you want to look for is a plane of symmetry that cuts through 1 atom and 1 bond, okay? Because you have an odd number of carbons in your ring. If you have an even number of carbons in your ring, you're looking at trying to cut through 2 atoms or 2 bonds, okay? So that's where you're going to start looking for those planes of symmetry when you have it. Notice here, when we do cut this plane of symmetry in this system, where we have it cutting through 1 atom here and 1 bond here, notice the OH is facing us, poking out, and then this one's also poking out. So these are going to be mirror images of each other. So we can see that. Even if we did that with the mirror image of the compound, we will also see that plane of symmetry in here. Notice if we did that same plane of symmetry in this one right here, this OH would be behind and this OH would be in front. Therefore, there is no plane of symmetry in this set of enantiomers, but there is a plane of symmetry in this set of enantiomers. So that makes it a meso compound, okay? So finding that plane, looking for that plane, and looking for the characteristics of the plane are the tricky part of the diastereomer sets, okay? So again, when we have an even number, we can either cut through 2 atoms or 2 bonds, okay? So in this case here with the cyclohexyl, the methyl cyclohexanol, we are actually using that plane cutting through a total of 4 atoms, okay? When we cut through that 4 atoms, notice that these, these are equivalent and these are equivalent, and because we have half of this atom above the plane and half of it below the plane, it's symmetrical. And half of this atom's above the plane and half of this is below the plane, it's symmetrical, okay? So that means that this cis isomer here is achiral because half of each of the atoms were there. Now, if we take the trans isomer, usually when in the 5-membered ring, we saw that one was achiral and one was meso and one was a pair of enantiomers. Here, because even though the plane is cutting through the same 4 atoms, we still have half an atom above and half an atom below, half an atom above and half an atom below, which turns this into a meso compound as well. So both isomers, even though there are two stereocenters in there, are achiral because of the plane of symmetry. Okay, so that's what I want to, kind of tell you about on those planes of symmetry. Now notice, when we did that before, we were cutting through a total of 4 atoms. If we have a different isomer of that cyclohexane, we can actually cut through 2 different atoms and also find a plane of symmetry. In, was it this compound here? We cut through an atom and a bond to create that plane of symmetry. Here we actually are cutting through atoms to make our plane of symmetry. Here we're cutting through 2 atoms that are not in mirror images of itself, but we still have, this is going to mirror this because they're both facing us. So this one is meso, but if we did the same thing here, this is facing out, this is facing back. Therefore, it is not a mirror image of itself. Therefore, we end up with a total of 3 isomers of the 1,3 cyclohexane diol. Okay, questions about symmetry planes. Okay, so in rings with 6 members, you're looking at cutting through bonds, 2 bonds or 2 atoms. With 5-membered rings, you're looking at cutting through a bond and an atom. And you have different isomers. The 1,2 isomer for a cyclohexane has different mirror plane than a 1,3 that has a different plane of symmetry than a 1,4. So those are things to look for when we're looking for symmetry. Okay, so I want to move on to chapter 6 goals, and those first goal is going to be nomenclature and the different isomers possible to us. And then we'll probably get to the reactions and leaving groups in SN1, SN2 tomorrow. But for now, I just wanted to introduce the topic with the nomenclature and the isomers possible. So the cool thing about alkyl halides, or adding a halogen to our hydrocarbons, is now we have a functional group, okay? The functional group is the halogen being able to leave because we formed a polarized bond. Remember, all of the halogens are more electronegative than carbon, therefore they can create a polarized bond where the carbon side of it is partially positive and the halogen side is partially negative. That's giving us functionality. So that's why I like to say this is a great introduction to our first functional group, and they're called alkyl halides. So basically all you have is carbon-hydrogen bonds plus this one halogen or more that gives us functionality. And again, these are sp3 hybridized carbons. They're trigonal, they're tetrahedral, but it gives us that new functionality that we didn't have before. Now, when we name these, we start with all of our same rules of nomenclature. And because halogens usually are easily removed, they don't change the parent name, okay? So whatever the parent was, if we only had a hydrocarbon, it would be an alkane, an alkene, or alkyne. And then we add the halogen as a substituent, okay? So if we just have one of them, we use the fluoro for fluorine, chloro, bromo, or iodo, and you list them in alphabetical order if you have more than one. And if you have more, if you have more than one type, you list them in alphabetical order. And again, if you have 2 chlorines, you would use the dichloro, 3 bromines would be tribromo, but you don't include the prefix when you do the alphabetization. You use the actual atom name, okay? And then just like before, we locate the halogen on the parent chain based on its numbering system, trying to keep the first substituent at the lowest number. So if we look at our lowest one here, we have 1, 2, 3, 4, 5 carbons is our main chain. So we have pentane. Our first functional group is on the lowest one, which is 2. So that means in alphabetical order, we have bromine before methyl. So we have 3-bromo, 2-methyl pentane. Okay. So, and if our alkane has, if our hydrocarbon is a double bond, the parent is now the hexene or the ene functionality, and so that is just the parent. All we have to do is identify where the halogen is. Now, in the last example here, by the time we get to the alcohols, which is one of our next chapters here, you'll see that alcohol actually changes the parent name. Okay, so we name it for the alcohol. And so, but the halogens will always be substituents. They will never change the parent name. So that makes it really good for us. And the fact that halogens are always substituents, we always just have to identify which carbon they're attached to. Okay, now, because some of these are used very commonly in industry, they have common names. And so there's a few common names that I think you should try to remember. They will be very, they'll occasionally come in as solvents and reactions, and they'll be kind of well known if you look at movies and other things. The first one is called dichloromethane, or CHCl2, okay? In a lot of halogenating reactions where we add bromine or chlorine to something, we're going to use a chlorinated or a halogenated solvent so that the solvent itself does not react. It does not participate in the reaction, but it does not react with the halogenating agent. So we use them a lot. And so if there's just 2 chlorines on it, we call that dichloromethane or methylene chloride, because a CH2 is sometimes called the methylene group, so we call it methylene chloride. The next most common is the trichloromethane, which is called chloroform. And you see that a lot in movies where the spies all put a thing of chloroform over somebody's mouth and they pass out immediately. Well, that's not true. It is used as an anesthetic, but it takes a long time to do. So you're fighting them forever. So don't do that. Anyway, so with the next one is trichloroethane. This is used a lot in the semiconductor industry to clean stuff. And in the last one is the tetrachloroethylene. So tetrachloroethylene is used a lot in dry cleaning. The old-fashioned dry cleaning was actually using tetrachloroethylene as a non-water solvent to remove dirt and oil. A lot of systems have switched over supercritical CO2, but you'll still see trichloroethylene used. Now, they do extract it completely out of your clothes because it's very expensive and they like to reuse it. So you don't have to worry about residue of that on your clothes, but it is used a lot in the dry cleaning industry. Okay, so the other common set of things that have common names are what we call freons. And freons are used in refrigeration systems, like your refrigerator and your car compressor and your air conditioner in your car. And they're used because if you take them and compress them and then release them, they absorb a significant amount of heat when they reduce pressure. Okay, because of the heavy atoms in there, they take away a lot of heat with them. So it's a very efficient way to do that. Unfortunately, they are ozone depleting because of the long-lived radicals that are formed in the high atmosphere. But they have common names, and they're based on the number of halogens hooked to a specific carbon. There's an engineering term for it. But one of the more common ones is called Freon 11. It's trichlorofluoromethane. And there's Freon 12, where you have 2 fluorines and 2 chlorines, which is dichloroethane. Okay, so the newest ones, the ones that are less ozone depleting, are what we call HFCs, or hydrogen fluorocarbons. So notice that those 2 at the bottom, the 134 and 141, have the halogens on them still, but they also have hydrogens on them. What that does is that makes them more reactive in the atmosphere, and so they actually are depleted in the atmosphere much more readily, and so they're better for the atmosphere overall, but we still need to find some much better system eventually. Okay, so let's do a couple quick names right here. All right, here, first thing I want to do here is let's just name 2 of these, and then we'll move on. So we have, our parent chain has 1, 2, 3, 4 carbons in it. So we have 4 carbons. We only have 1 substituent, so we're going to name it from that side. So we're going to name 1, 2, 3, 4. So 4 carbons is butane, Okay, we have 1 chloro, and it's on the number 2 carbon, so it's 2 chlorobutane, okay? So that's our naming structure there. Are we done? I see a carbon with 4 different groups on it, right here. So we have an ethyl group, a methyl group, and we have an understood hydrogen. So we have to name it whether it was R or S. So using our hand, we can say the hydrogen is facing back. So our index finger is going to be the chlorine. Our right thumb is going to be the ethyl group, and the index finger will be, sorry, the middle finger will be the methyl group. So that's 1, 2, 3. That's clockwise. So that makes it R. So if we were to name this correctly, it would be an R2-chlorobutane. Okay. Luckily, the next one is easier to name because it doesn't have an R or S on it. And we have 1, 2, 3 carbons total as the longest chain, and then a substituent. And let's see, we want to number it so the substituent's on the lowest carbon. So the bromine would make it the first carbon. So that's going to be 1, 2, 3. So 1, 2, 3 is propane. And then we have a methyl group and a bromo, M versus B, B's first. So we have 1 bromo, 1 bromo, 2 methyl, dash methyl propane. Okay, so again, it's just a substituent. Use all our rules. It's just going to be and arrange them in alphabetical order. Go ahead and do the last 2 on your own, and we'll move to the next slide here. Okay, so when we look at identifying the different halocarbons, they have different reactivity based on the number of carbons that carbon that's attached to has. And so we want to classify our halocarbons, or our alkyl halides, by how many carbons are attached to the carbon our halogens on, okay? So what that means is that for our simplest one here, it would be methyl. That would be a CH3 with bromine on it, okay? So we have 1 carbon, and there are no other carbons attached to that carbon, and we call that as a methyl halide. Okay, methyl halides are really reactive because, number 1, we have a polarized bond. Number 2, we only have hydrogens that get in the way of anything else coming in and reacting. So they can be very reactive to certain substitution reactions, which we'll talk about next. The next classification here is what we call a primary. What that means is we have 1 carbon attached to the atom that the halogen's attached to, okay? So that's what that primary means, 1 more carbon that's attached to it, okay? So the next one would be 2. So if we look at the carbon that the halogen's attached to, it has a total of 2 carbons to it. That gives us our secondary. And if we look at this carbon right here, our halogen's attached to, we have 1, 2, 3 carbons on it. That's our tertiary, okay? This becomes important in the next set of our experiments because having groups over here on these carbons here change the reactivity of that alkyl halide, okay? When it changes the reactivity of our alkyl halide, it'll follow a different mechanism. Okay, and we can think of it as kind of a spatial thing, is that if there's only hydrogens here on this methyl halide, there's not very much stuff to get in the way. Hydrogens are kind of small. You can have something come in and hit it and displace that bromine fairly easily. By the time you put 1 group on there, you know, okay, I have to avoid 1 carbon, but I still have 2 hydrogens. And so I have a big opportunity, let's call it, you know, if I have my compound come anywhere from this direction over, I can still kick out that bromine. By the time you start to put that second carbon on there to give you your secondary here, now you only have one hydrogen back here. So your little cone where you could actually have things come in and attack gets a little bit smaller. And by the time you put 3 of them on there, you have to have pinpoint accuracy to come through and kick out that halogen here. So in general, methyls are very reactive to substitution reactions because there's no sterics involved. Primaries, we start to get a little, carbon is starting to get in the way, but we still have 2 hydrogens. Excuse me. Secondary and tertiaries are much less because we're starting to have carbon get in the way. Okay. So this is a demonstration by looking at these space-filled models. If you have just this ethyl group with a bromine on it right here, you have that methyl group there, but it's not just the carbon itself being bigger, it's the fact that it has those 3 hydrogens attached to it as well. Okay, so let me actually do it in yellow here. So right here in yellow and yellow, those are those 2 hydrogens there. They aren't really blocking the carbon that the halogens attach to very much. But by the time you put 3 of them on there, we now have very little space in between those methyl groups to actually come in and attack. Here we can attack anywhere in this area here, and we can displace that. But here, by the time you get 3 of them on there, this is a very narrow window for you can have to have a molecule come and attack it back. So we have a steric factor with this, and that's why we have methyl is most reactive, followed by primary, secondary, and tertiary in that order. Okay. Because of that, we have to pay attention to whether it's primary, secondary, or tertiary, because it will change the mechanism of our reaction. Okay. We will start to go from a bimolecular reaction where you have one thing coming in and knocking out the other, to having to form a different species, have it form the carbocation before it will react. Okay, so that's why it's very important to keep track of primary, secondary, and tertiary when we're looking at the types of hydrocarbons we have. Okay, and so this is just a variety of it in this first one here, because we have the 3 different carbons attached to the carbon our chlorine's on. That makes it a tertiary. We only have 1 carbon attached to the carbon with the thing, so that's our primary. We have 1, 2, so that's a secondary right here. And here we go, we have it in a ring here, but we have an understood hydrogen sticking up at us, so this is also a secondary alkyl halide and will react as a secondary alkyl halide. All right, questions about nomenclature, primary, secondary, tertiary? Yeah, I'm not going to start that one now. Okay, any questions on that? Okay, so I've posted a lot of the lectures already. Any other lectures that haven't been posted already, I will post today. I think I'm all the way through chapter 7 on YouTube here. Chapter 6. No, chapter 7's not on here yet. Okay, I will post chapter 7's today. Why aren't they up there? Okay, so right now, all of chapter 6 is up there. That's looking at chiral compounds and identifying enantiomers, etc. The Alkyl Halide videos will be up there soon. And it introduces 2 things. Number 1, it introduces the idea that alkyl halides are our first functional group. It starts us looking at things that are called leaving groups. So if they're functional and they leave easily, the reaction might go faster or react in a certain way. If they don't leave easily, maybe they react in a different way. And so we kind of have to start balancing these things of leaving groups and whether or not it's nucleophilic, whether or not it has a negative charge. These are the types of things we'll start looking at in Chapter 7. Okay, we're right about 135, so that's pretty close to my 140 target here. If anybody has any questions, I can answer that now. If not, you can go ahead and start looking at the videos. Homework through Chapter 8 has been posted, I believe, on Top Hat. Yeah, questions and self-test questions have been posted for Chapters 5 through 8 on Top Hat. So those are available to you as well. Okay, I'm going to stop recording so I can post this. And then if you want to hang out and ask a question or two, that's fine.